You, Sir Isaac Newton, and Albert Einstein all have one thing in common. You also have it in common with all these geniuses, as well as these Nobel laureates. And no, it's not genius. But if it is not that, then what could you possibly have in common with the man who wrote Principia Mathematica and the one who discovered special and general relativity? I will answer this question by showing you 3 laws of growth of science. So, what is the first law of growth? This graph shows the cumulative number of papers published in physics since 1800s, as well as chemistry, medicine, and biology. There is a common feature among them. They all have exponential growth. We can characterize each exponential growth with its growth rate. To calculate the growth rate, we can take the natural logarithm of exponential growth and visualize it in log linear graph. For a pure exponential growth with constant growth rate, the result will be a straight line. But for our data, the result will more or less fit a line. Here we can see the log linear graph for the number of publications in each field and the fitted line to the data between 1900s to 2024. One advantage of log linear visualization is that we can see slight changes in growth rate as the slope changes. For example, medicine has a slower growth rate between 1845 and 1935. But there is an even simpler way to understand the exponential growth. We can characterize it by the amount of time it takes for the growing index to double. Then the number of publications in physics doubles every 9.4 years. Chemistry doubles every 8.5 years and biology doubles every 9.2 years. Medicine is no exception and it doubles every 9.4 years. Note that we do not have any criteria on which papers to count. Such criteria will increase the doubling time to 15 to 20 years depending on how high we set the bar. But for now, this will suffice. So we saw that scientific productivity has grown exponentially, at least for the past 2 centuries, with a doubling time of 10 to 20 years. Now, how about scientific manpower? We can estimate the scientific manpower by counting the number of PhDs awarded each year. We're assuming that every PhD is a scientist and all scientists have a PhD, leading to a higher bound for number of scientists. In the US since 1800s, we see that the doubling time is about 9 years. We can compare this growth with the population growth in US and notice how much faster the number of PhDs grows compared to population. Currently, US's population doubles every 75 years. For any other country, the doubling time will differ, but not the exponential growth. Now that we have established science is growing exponentially, what can we say about features of this exponential growth? Well, first, this empirical law fits any science index such as number of publications, number of scientists, number of universities, and so on, that we define and measure over a long term. Even if we define our index carelessly, so long as the period is a few centuries, we can still observe it. Second, the exponential growth has been happening for a while, at least since 1600s. Beginning 1660, scientists started forming their scientific societies and founded their periodicals. They started to publish papers instead of their usual output, books. Since then, the number of journals and number of scientists has increased exponentially. If we take 1 million scientists in 1960 along with the 15-year doubling time, we can work our way backward to 1800s. With the doubling time of 15 years, every 50 years the number of scientists increases tenfold. So, in 1900s we had about 100,000 scientists, in 1850 we had 10,000 scientists, and in 1800s we had 1,000 scientists. From this point of view, we can agree with Price that the Industrial Revolution was part of the exponential growth of science and technology. It was inevitable even though some may argue otherwise. It seems that the society, politicians and monarchs had to adapt to the inevitable. Lastly, the third feature is the rapid growth, which leads to a high immediacy constant. It is the percentage of science ever existed that is present now, and I will show you later that 80 to 90% of scientific manpower and production ever existed are happening right now. We can compare science's immediacy constant with the population's immediacy constant. It is estimated that 117 billion people have ever lived. 8 billion are alive right now, giving us an immediacy constant of 7%. For the world population to reach 50% immediacy, we will need another 260 years, assuming a constant doubling time of 50 years. So, science has been growing, and it has been growing explosively fast. We can argue that most of the great people who ever lived are dead now. But there is a difference between history and history of science. When we talk about politics and war, there is much more to discuss. A longer past, if you may say, but the science occupies much less space in time. Now, will science grow like this forever? The answer is no, it can't, and here is why. Let's take another look at the number of PhD holders in the US. There are about 5.8 million PhD holders. This means that in a decade, the number of PhD holders will reach around 12 million. In half a century, we will have 186 million scientists, while the projected population will be about 402 million. This means that we will have 5 scientists out of every 10 Americans. Even if we use the current doubling time of 75 years for US's population instead, assuming it will remain the same, we will get 530 million people in 2075. With this, we arrive at 4 scientists for every 10 Americans. And this is an absurd amount, wouldn't you say? This growth cannot go on forever, and it must be capped. There are 2 reasons for this, which I will prove them in the future episodes. First, there is a limited number of people we can pour into science because only a small percentage of population can become scientists. Second, producing a research paper costs money, and our wealth is not unlimited. To make matters worse, as the system grows, the cost per capita of science, meaning cost per scientist to keep them going, increases exponentially and has its own cap. Therefore, there must be a higher bound for the growth of science. In nature, almost all exponential growths are part of a logistic curve, the S-curve. It is very rare to see a growth curve that is not logistic. This curve has an exponential beginning and is capped at a maximum value. The difference between exponential and logistic growth is in the growth rates. In the case of exponential growth, the change in the cumulative population, PhDs, number of papers, or any other reasonable index in a year is equal to the growth rates times the population at the beginning of the change. In logistic growth, the growth rate is multiplied by growth limit minus population divided by the growth limit. Initially, the effective growth rate is almost maximum. But as n approaches L, the growth rate drops linearly to 0. So science started with exponential growth as part of a logistic growth, and it will reach a limit. Now, what are the features of logistic growth? Let's look at the beanstalk growth. At the beginning, it grows exponentially with the doubling time of 1 day. It will reach a maximum height at about 7 days. At some point in the middle, the beanstalk is at its 50% of maximum height. This is the inflection point where the exponential growth has already slowed down and is changing direction. The growth will continue for about 3 doubling times after inflection point. The exponential growth stops at about 3 doubling times before the inflection point. So, for every logistic growth, we can define a mid-region around the inflection point with 3 doubling times on each side, during which the system transitions from pure exponential growth into the logistic growth and then into the saturated state. In the case of beanstalk, the transition period is from day 1 to day 7 with day 4 as the midpoint. Now the question is, when is science? This graph shows the sum of all papers published in physics, biology, chemistry, and medicine. Again, we can see the exponential growth with doubling time of 10 years. If we already passed the midpoint in 1950s as Price assumed, then we should have reached the saturation in 2000s. But our data does not show such a slowdown. Only recently, Asghar Qasemi and his colleagues showed a slight decline in the growth of number of journals. Where we can agree with Price is that we have passed the midpoint of science's growth. But how close we are to the saturation may not be clear yet. Then how can we tell science is nearing its saturation state? Scientific creativity is not the only field logistic growth applies. You can see it in other productive fields, such as motor vehicles in use as a representation of car manufacturing, coal, copper, zinc, and other mining production, and railroad track building, to name a few. We can see how logistic growth behaves as it approaches the saturation. Copper, zinc, and coal production oscillate as the production nears saturation. This is because the system senses the decrease or increase of the growth rate and tends to correct it but overshoots. In the case of vehicles in use, we can see the revival and escalation of growth after a period of saturation, indicating a breakthrough in the economic state of the country. The same phenomenon can be observed in particle accelerator physics, number of universities in Europe, and cumulative number of elements discovered in time. Each increase in particle accelerator energy is due to a technological breakthrough. The escalation in the number of universities in Europe is because of the Renaissance. The number of elements has 2 breakthroughs. One is due to innovations of chemical techniques, and the other is because of leaps in nuclear physics techniques that have facilitated discovery of radioactive elements. We can use the escalation pattern to predict when we need a breakthrough to revive the growth. AI's growth, whether in number of neurons, weights, or computing power, follows a logistic growth. It seems that the scaling efforts in AI led by OpenAI leading to ChatGPT-5 model has reached its saturation as GPT-5 performance was only slightly better than its predecessor, hinting to a need for technological or scientific breakthrough. Lastly, in the case of railroad production in the US, as we can see, the growth completely dies off sometime after 1930. So these are the behaviors we can expect from a logistic growth. First, after reaching saturation, a breakthrough may happen and the growth can go back to exponential and then logistic growth. Second, the curve will die because the growth stops or the system changes in such a way that the index we are measuring is not valid and can't be measured anymore, and so the curve itself stops. Third, it can oscillate before reaching the saturation, and fourth, it can oscillate without ever stabilizing. Now, what is it you share with these great scientists? It is science's high immediacy constant, that despite living centuries apart from each other, you all observe 90% of scientific discoveries being made during your lifetime. You all live when 90% of scientists are alive. To show this, let's do some arithmetic. We assume that a scientist is active for 45 years. We can take the doubling time to be 10 years. So we get 4.5 doubling periods within the 45 years. This means that for every junior scientist starting now, we will have about 23 scientists at the end of the 45 years with 22 active scientists out of 23. This is about 96% of all scientists in 2070. Even if we follow directly Solla Price, whose Little Science Big Science book is a major source for this series, and take the doubling time to be 15 to 20 years, we will end up with 87 to 79 active scientists respectively. Replace the scientists with scientific publications and you will still get the same result. Then what is next? In the preface of his Little Science Big Science, Price writes, I shall attempt to develop a calculus of scientific manpower, literature, talent and expenditure on a national and on an international scale. From such a calculus, we hope to analyze what it is that is essentially new in the present age of big science, distinguishing it from the former state of little science. In chapter 1, which we talked about in this video, he makes the distinction between little science of 1900s and big science after 1900s by describing the science since 1600s. He argues that we can't use big projects of the past to distinguish them because big projects always existed, and that the big projects of today are dwarfing the Egyptian pyramids. So he provides the statistical evidence we saw in this video to define the growth of science to distinguish between the little science and the big science and the transition from former to latter. If the era of 1600s to 1900s is, as Einstein described it, the happy childhood of science, or as Price calls it, the little science, then we must be in the transition to the age of maturity of science, the age of big science. As scientists, engineers, and creative and productive people, which I can propose includes almost all human endeavors, we and our productivity are part of this logistic growth. Now the questions are, how is this scientific output distributed among scientists? Is there such a thing as equity? And what should you expect to get from your hard work? I will answer these in the next episode.